Hello, everyone. Welcome to this second session of Multiple Universes. I'm James V. Barbieri, Associate Program Director here at the Power Center, and I'll be your host for today. As a host, I'm here to help you throughout the call, so any problems, technical or not, feel free to just drop me a message in the chat. Before we begin, I'd just like to go over a couple of Zoom rules for this session. First of all, we ask participants to turn off your microphone during the presentation, just to ensure good quality audio. But at the same time, we do encourage you all to turn on your camera. During Q&A and discussion, if you'd like to ask a question, you can use the raise your hand function on Zoom, which can be found at the bottom right of your screen under reactions, or physically raise your hand, and if I spot you, you can ask your question. Of course, if it makes you feel more comfortable, you can always ask your question in the chat and I can read it out for you. Yes, and finally, the session is recorded for archival purposes and for you all. The session will be uploaded to Vimeo in about 3 days, so you should all receive the link for that. And now we can begin today's session. Today, I am very glad to introduce Paul Tappenden. Paul teaches philosophy of science and to physics students in Grenoble, France. Paul did his first degree in philosophy and psychology and did his PhD on trying to relate an important current debate in philosophy of mind with ideas in the Everett interpretation at King's College London. So yes, today Paul will talk about dendritic quantum mechanics. Over to you, Paul. Welcome.
Okay, well, thank you, James, and I'm very happy to be here and have this opportunity to try and talk about some rather arcane ideas with people who will be not all familiar with some of this, and so I shall try and make it as clear as possible. I'm going to begin by connecting a bit with what Bernard was saying yesterday, because towards the end of when he was talking, he talked about Everett and splitting, which will mean more to some of you than others, and he was and that's exactly what I'm going to be talking about, and he was sort of reflecting on the connection between that and what he was talking about. So first of all, let's say what I'm going to be talking about is very much to do with how we understand what's going on inside our bubble. If there are lots and lots of different bubbles, then what I'm concentrating on is what's going on inside our bubble. Okay. Now, what I'm going to be talking about is often called interpretation of quantum mechanics, and this is the so-called Everett interpretation is one of them. There are others. In fact, at the moment, discussion about interpretation of quantum mechanics seems to get more and more dispersed. Different ideas come up. What I'll be talking about is what's often called, is in the tradition of realism. I mean, there are other views quite different which are in that tradition as well. One of them is sort of stochastic theory. Another one is pilot wave theory. We'll be coming back and talking a bit more about these later on. And those two and the Everett interpretation, really the sort of main realist interpretations, they hang on to the idea that there's an external world out there, and what we're trying to do is understand that external world, how that can be in that way and create the quantum phenomena. There are plenty of other views as well, and there's a sort of variations on the view that quantum mechanics actually undermines the traditional concept of an external world, but I won't be talking about that at all. But then, as far as the other bubbles are concerned, as Bernard was explaining, the other bubbles are where the physical constants are different. And in current physics, there's at least 19 and maybe 26 or more constants of nature, which, as Bernard was explaining, seem to be fine-tuned to our existence, or to something or other. Anyway, we wouldn't be existing if they weren't very finely coordinated, let's say. But nonetheless, the idea is, as it stands, that in those other bubbles, it would be quantum mechanical evolution which would be going on. So what's going on in our bubble what I should be saying about what might be happening in our bubble would be relates to the other bubbles as well. And then there was another aspect of the connection which I thought was interesting, which Bernard brought up. It was talking about the final theory. Okay, so it was saying if we get to a final theory, we'll be able to either understand that there are these different ways the constants could be, and there are loads of bubbles, or we might end up finding that actually there's only one theory which can work, and so that they all have to be the way they are, and that's it, which would be absolutely remarkable if it were like that. In fact, Leibniz, the 18th century philosopher Leibniz, he's famous for talking about this being the best of all possible worlds. If this final theory were to explain all the constants, that they must be the way they are, it would mean that our world is the only possible world, if you like. But at the same time, there's been a lot of hype about final theory. There was a lot of hype at the end of the last century about we're on the edge of finding the final theory and this sort of thing, which was sort of understandable given the enormous progress which was being made. I mean, with the Big Bang theory coming up in the 60s and being developed very quickly. In the 70s, the standard model in particle physics, the quark theory, was falling into place. The beginning of the 80s, string theory, which seemed to offer ways to unite quantum mechanics and general relativity. So understandable, but at the same time, maybe it was a bit over the top, because perhaps we're on the way to a final theory, if we ever get there. Perhaps we're coming from a pretty low base, because when you think about it, 400 years ago, nobody understood what we think of as the basic rules of mechanics. I mean, the pendulum clock wasn't invented until the middle of the 17th century by Huygens. 100 years ago, nobody knew how the sun shines. Nobody knew the mechanism of how the sun shines. We didn't discover how elements are forged in stars until Hoyle's work in the 1950s. So goodness knows. I mean, we've got, as Bernard was explaining, 5% of the universe, the observable universe, seems to be matter that we have any idea about how it works. We've got dark energy, dark matter, which seem very obscure subjects. And for instance, this business about the inflation, arguments for inflation, and there seems to be some really interesting evidence for some of the predictions of inflation theory in the background, radiation. But one of the things which inflation was found to be useful to explain is why we don't find things called magnetic monopoles in the universe. It was supposed to explain why these are because according to sort of physical theories, there ought to be such things, but we don't find them anywhere. So inflation helped to explain that by saying, well, they were created very, very, very early after the Big Bang, and then they got spread out by the inflation. But the interactions which, according to this quite speculative theory, create magnetic monopoles are taken to happen at energies which were a trillion times more than the highest energies in the CERN accelerator. So Bernard mentioned, future accelerators, which hopefully will get higher energies, but will there be the money to build them? Maybe people will discover sort of amazing ways we haven't thought of to build accelerators much more cheaply, but there's a long way to go before we can hope to create a magnetic monopole and accelerator. And so a long way to go before we can sort of say that, well, okay, this part of current theory has been confirmed. And then that takes us back to the first 10 to the minus 36 of a second after the Big Bang. But according to current theory, you can go on back to the 10 to the minus 43, the Planck time, 10 to the minus 43 seconds. So, and that takes us up to an energy which I think is in the order of 1 trillion times more. So there could be a long, long way to go towards the final theory, and it could take centuries and millennia, who knows? So maybe we should sort of calm down a bit about finding final theories. But I do agree with Bernard that if there were to be a final theory, then surely it would have to include understanding what goes on inside the bubbles plus everything else. So presumably, whatever interpretation of quantum mechanics emerges and makes sense, if one does, that would be part of the final theory. And so, yeah, we might find a connection there, but it's certainly true what he says, that what I'll be talking about is taken entirely in terms of, we're not talking about different values for constants or anything like that. We're inside one of Bernard's bubbles. And so we're inside a sort of multiverse, which is inside another multiverse, if you like, if it exists. But that other multiverse is, if you like, elsewhere. And this multiverse that I'm going to talk about is sort of much closer to home, as Bernard sort of implied. It impinges much more directly on our how we conceive of the world we're actually living in. And then there was one other thing I wanted to talk about before starting what I planned to talk about, which is Mel's comment about being a shut up and calculate physicist, which is fine. Everybody's free to do what they want, of course, but I mean, one thing to say is, well, it seems to be it's calculation which has led to things like inflation theory, N theory, that sort of thing. Okay, certainly there are people saying that it's calculation which has sort of gone wild, which has gone sort of unconstrained, and which is not getting enough feedback. There is some feedback, as we said, from the background radiation on inflation, but anyway, there's still deep disagreement on all that. But at the same time, so that sort of, I mean, what Bernard was saying about these bubbles with different values and so on, that is a sort of product of the calculating process. When you move over then to talking about the anthropic principle and the relevance it to other things like where, you know, how did Bernard put it? What is it that the universe is sort of fine-tuned to create, and maybe it's consciousness? So then we're in the domain of philosophy. Okay, we're certainly not in the domain of shut up and calculate. But you know, physicists don't have to calculate all the time. They can have some time off. As Bernard said, it was a Saturday evening, so maybe there's time to think about. There are questions to do with physics and what physics is about, which perhaps physics itself can't answer, and it needs some help from other domains, such as philosophy, or what philosophers call metaphysics. So at this point, yeah, I would. There's on the subject. There's Richard Feynman, who is outstandingly good at calculation and got a Nobel Prize for it. And has wrote some wonderful books. This is a quote I'm going to give you from a book of his called The Character of Physical Law, which is a great book to read. He says, do not keep saying to yourself if you can possibly avoid it, but how can it be like that? Because you'll get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. So even the great Richard Feynman, he's saying, look, nobody knows how the world can be in such a way that it yields these phenomena which we're seeing, as phenomena as simple as the two-slit interference experiment, which I expect many of you know about. I mean, these are very strange phenomena, and nobody yet knows if there is an external world, how it could be like that. And so he's quite right. If you want to do physics, then you better not spend too much time thinking about that, because you will, it'll take your mind off the physics, and you'll go into what is so far turned out to be a blind alley. Perhaps one can hope that it won't always be blind. It seems to be an alley which is sort of ramifying as it goes along. But perhaps there is some light at the end of the tunnel, and somebody will get there in the end. So again, there's space for physicists to think about that in their time off, and there's space for philosophers to think about it full time if they want to. Okay, so at this point, I think I'll ask James to take us to the first slide.
Sure.
Okay, so I'm calling this dendritic quantum mechanics. Now, it's not a term which is much in use for familiar, but what I'm stressing is, in actual fact, what goes under the title of the Everettian interpretation. Actually, there's a very significant split, and within the split, I mean, it's like any sort of church, there are all sorts of little side issues, and hard to find two people who really agree on everything. But there is a very significant split, I think, on one aspect of it. Well, I didn't really mean to be using the word split, but I mean, splitting definitely comes into it, and splitting is what I'm going to be talking about, and that's why I call it dendritic, because it's splitting like a tree. And so this image in front of you, what that's supposed to symbolize is the Earth splitting off into every future which we would normally think of as physically possible. We'd normally think of, okay, we've got one future, don't know what it is, it's somehow selected from a range of possibilities. What this is saying is, well, all those futures which we thought of as possibilities, they exist, and that's what's going to happen. And so you can see that, again, another allusion to what Bernard's saying. He's saying the universe was always growing, has always been growing. Our view of the universe has always been growing. And quite rightly, through the history of astronomy and cosmology and so on, it seems that the horizon is ever expanding. And when we reach the limit of the horizon that Bernard was talking about, well, then there are all these other things beyond that horizon. So this idea of this ever more astounding enormity of it all. Well, we're just inside one bubble. We were just inside one bubble where the constants are what they are. And yet this view is saying that within this bubble, there's this constant ramification, enormous ramification from moment to moment into all these possibilities. So this is another way in which the universe is growing, if you like. And yeah, and a final allusion to Bernard, remember his eye. This is very much about the eye was what the observer, situated inside the universe, if you like. What Jeff Barrett, who is a very prominent theoretician into the interpretation of quantum mechanics, has studied a great deal of the Everett interpretation, but has a very healthy skepticism. He's certainly open to all other things as well. He talks a moment about the importance of an interpretation of quantum mechanics which includes what he calls the situated observer. And this is very like the idea of Bernard's eye, which is sort of in the center of things. In the center of things metaphorically, let's say. And so as we move on now to talking about dendritic non-mechanics, I'm going to another little quote. This is from Physics Today, a physics journal, from 1971, exactly 50 years ago. And here this was an issue which brought together a number of articles by different people under the title Quantum Mechanics Debate. And the subtitle was, "Not everyone agrees with Bryce DeWitt that the acceptance of quantum theory implies belief in a continually splitting universe." Well, 50 years on, not everybody accepts it either. I should say that Bryce DeWitt was one of the person who really put Everettian theory on the map. I mean, Everett himself, there's an interesting book available about his life. Basically, he sort of said, oh, well, you know, what is it? A curse on all their house. Nobody took him seriously. He went off and worked on atomic bombs and computer programs and made quite a lot of money and sort of let it lie. But Bryce DeWitt, towards the end of the 60s, took an interest in it, and he actually refers to the theory as the Everett-Wheeler-Graham theory. John Archibald Wheeler was Everett's supervisor, and Neil Graham was somebody who took an interest in it. And DeWitt and Graham went on a couple of years later in 1973 to publish a book, they edited a book which included writings from them and from Everett. So there was what's called Everett's long thesis, where there's more details about what Everett did. And really that's what began to put Everett on the map. It took a while to get going, but as the 80s and 90s came along, there was more and more interest. Okay, so now we can go to slide 2, James. Thanks. So, a lot of dissent, 50 years of argument, and still no conclusion. And this, it's not a matter of whether, there's not only a conclusion about whether this is a plausible way to interpret quantum mechanics. There's genuine disagreement about whether the idea is even intelligible. I mean, it's incredible, but you know, 50 years on from that article in Science, in Physics Today, and well, I don't know, nearly, what is it, 60, 70 years since Everett was working. Still, there's no agreement, and there are very well-informed people who don't think it's intelligible. So I'm not going to be attempting to convince you or in any way sort of suggest to you that, well, maybe I will be trying to suggest, I'm not trying to convince you that this is a sort of the right way to interpret quantum mechanics. All I'm going to try to do today is convince you, I hope, that it actually is an intelligible idea. And so I'm going to talk now for probably about 35, 40 minutes, something like that. There should be a good, the best part of an hour for discussion afterwards. And so what I'm going to be doing is developing an argument, basically, and it's important that I take you with me on the argument. So really, if there's a step in the argument which that doesn't make sense to you, do stop me and we'll try and clarify it, because what I want to do is go through the argument that it's intelligible, and then when we're satisfied that, okay, we're reasonably satisfied that people agree that it, okay, could be intelligible, then we can go on to the second part of what I want to do, which we'll see, which will come along later. So now we can go on to the next slide, James. Okay. So we're talking about the situated observer in the bubble, inside the bubble. And in the Everettian tradition, we often refer to the situated observer as Alice. And it's very appropriate, really, because it all gets very strange. And in comparison with Alice in Wonderland is definitely comes to the fore. So Alice pulls back the curtain. What does she find? She finds not a door to a secret garden, she finds a Stern-Gerlach apparatus. And this Stern-Gerlach apparatus is something which can measure the spin of an electron. Now, spin is a complicated sort of thing, but you can just, it's not necessary to understand the details of it. Just think of the electron as like a little ball which is spinning. And what it can do, this apparatus, is relative to some axis, let's just suppose the vertical axis, it can tell whether this electron, which has been sent to it, is spinning up or spinning down. And that simply means that if you're looking down on top of it, is it rotating clockwise or anti-clockwise? Just a convention of whether you call it up or down. Okay, next, James, please. So in comes this electron, which has been prepared in advance into a certain state, into the apparatus. And it says to Alice, measure my spin. Next. And according to quantum mechanics, the way that the electron has been prepared going into the apparatus, there's a probability of 1/3 of Alice finding spin up, that's you, and a probability of 2/3 of spin down. Now, quantum mechanics is always in the business of predicting probabilities, and it does it with a high degree of accuracy. Some probabilities can be calculated to about the 10th decimal place and confirmed. And of course, the way you confirm them is with statistics. I mean, these experiments in CERN, you know, there's lots and lots and lots and lots of data, and you do a statistical analysis on it, and that's how you get to confirm that the predicted probabilities are actually confirmed in the experiment. Okay, so that's what quantum mechanics tells us incontrovertibly, and it's the gold of quantum mechanics is the probabilities that it comes up with. On to the next slide. Okay, so we have what I'm going to call conservative quantum mechanics. Conservative quantum mechanics says that Alice has a single future. Either she's going to find up or she's going to find down exclusively, right? One or the other. And what says this? Well, amongst the theories which say this, stochastic theory, again, I'm not going to go into the detail, it'll come up about the details of this perhaps later on. Stochastic theory, pilot wave theory, and also many worlds theory with divergence. Now, there are some people who I'll mention names later on, who take themselves as Everettians, as developing Everettian quantum mechanics, and yet they don't think that Alice. They think that Alice will see one or the other. It's because they've got this concept of divergence, and I'll explain that later on. So we go on to the next slide. Okay, so dendritic mechanics, in contrast, says that Alice has multiple futures. Alice will see up and Alice will see down. And so this is many worlds theory with fission, okay? And so we'll go on now to the next slide. And fission is what I take to be Everett's eureka idea. It's this idea that Alice splits into two branches, okay? And this is how he put it in a few lines. I think it's all summed up in those few lines, which, hold on, I've got to go to, what the quote is a bit obscured, so I'm going to just go to it. Okay, so I can read it. So I'll read it out to you. What these few lines, it has to be said, were in a footnote to Everett's seminal paper, which was his thesis. And why was it a footnote? Well, people have different opinions why it was a footnote, but it seems to me most plausible it was a footnote because his supervisor, Wheeler, just couldn't bear Everett actually expressing the idea so boldly, and there are reasons for that, and there's a lot of literature on why. But anyway, here's the broad idea. All elements of a superposition, all branches, are actual. This total lack of effect of one branch on another also implies that no observer will ever be aware of a splitting or any splitting process. So what's he talking about here? He's talking about the superposition is, the superposition has two elements here. And these are the elements of the superposition. One element is the branch of weight 1/3 where Alice is seeing up. And the other element is the branch of weight 2/3 where Alice is seeing down. And these elements consist of what Everett called relative states. So on the left, Alice is in the state of seeing up, and the electron is in the state of having spin up. And on the right, Alice is seeing down, and the electron is in the state of spin down. And these branches have weights, okay? And what are these weights? Well, these weights are quantitatively, they're exactly the same as the probabilities. They come directly from the figure which gives you the probability in normal quantum mechanics, but they're weights. I mean, I think of the branches as like, imagine that you're inside the trunk of the tree, and you're looking at these branches which have just, two branches have split off. And one branch has a cross-sectional area which is twice the other of the other one. It's that which gives you the quantity of the weight, okay? So you've got one branch where she's seeing spin up, which is smaller than the branch which is where she's seeing spin down, and the cross-sectional area of the down one is twice that of that one, and adding them together, you come to the weight of the branch which she was on before she split, because of course this splitting goes on and on. Alice, according to this view, Alice arriving at doing the measurement as she split off from the previous Alice's and so on. So if the branch weight is 1 for Alice when she does the measurement, it's 1/3 when she finds up, and it's 2/3 when she finds down. So we go on to the next slide. So two crucial questions this poses. In the first place, how can Alice become Alice U and Alice D? And how can branch weight be probability? Because if we can't make sense of either of those questions, then it looks like the whole idea is completely unintelligible. We go on to the next slide. Okay, so first question, how can Alice be Alice U and Alice D? So what's the problem? Alice U and Alice D are distinct subjects having different experiences, so Alice can't be identical to both of them. Alice U isn't Alice D, she's seeing up, Alice D is seeing down. So it's just logically impossible for Alice to be both of them. She can't, if she's one of them, she isn't the other one, and vice versa, okay? Now, this problem is this idea, if you like, of a person splitting in two goes back quite independently of any talk about quantum physics. it was discussed quite a lot in the 70s and 80s by philosophers. In particular, one of the outstanding ones was Derek Parfit, who's now dead, but he had a famous book which treated on the subject, and it was actually inspired really by split brain operations in the 60s. You know, these operations where the surgeons cut on epileptic people who have epilepsy. Their treatment was to cut the corpus callosum between the hemispheres, and it was found afterwards with quite sophisticated experiments that these two hemispheres seemed to have the minds of two people who were independently. You didn't know what the other was doing or what the other was thinking, and there were quite sophisticated experiments which sort of seemed to confirm it. And so this raised the idea, well, okay, is personal fission possible? If it is possible, then, you know, how do you understand it? And really, because of this problem about identity, I mean, Derek Parfit came up with, well, if it is possible, then you have to drop the idea of personal identity. And he got quite Buddhist about it, and he's had this famous sort of slogan that identity isn't what matters in survival. The idea is that caring about the future, you know, this apparently egotistic caring about the future, you can't be caring about you in the future, because the idea of you, the identity being the same in the future, doesn't make any sense if this fission is possible. And then in this tradition, again, completely independently of any thought about Everett or anything like that, Theodore Sider, a metaphysician, came up with this paper, this seminal paper, who's generally known as Ted Sider, so I'll refer to him as Ted, with this wonderful title, All the World's a Stage. Why does he say that? Well, it's because what we're trying to understand is how you can, okay, we're going to be applying this to fission, but before that, we were just talking about how you understand identity of a person or an object through time. And what he proposes is this, what was called stage theory, hence the title, and what has come to be known as temporal counterpart theory. For those of you familiar with it, it's related to so-called modal logic, modal theory, how you talk about possibilities. It's, if you like, the logic of possibility. So, not a million miles away from what we're concerned with, but at the same time, this is developed quite independently. And so, according to this theory, which Sider put forward, a subject or object is a temporal part of its history, a temporal part of its history. It's a stage in its history. Earlier and later stages of its history are its temporal counterparts. Okay, if we go to the next slide. So, how does this work? So, Ted now, he's not the same person he was and he will be. He was Ted yesterday and he will be Ted tomorrow. Ted yesterday, he's not any of the people he will be. He will be Ted now and he will be Ted tomorrow. That's the day after tomorrow for him. And Ted tomorrow, he's not the same person he was. He was Ted now and he was Ted yesterday. So the idea is that an object or person extended in time, what it is at any time is its stage in its history. And it's not what the other things that it was and that it will be, but its persistence is explained in terms of its having this relation of temporal counterpart to its a past object or individual or person or a future one. So go on to the next slide. So this has some very counterintuitive consequences, which, and when Ted Sider introduced this idea, he got quite a lot of people got fairly sort of dismissive about it, and there was a good deal of discussion, but it has survived because the thing is, it is very counterintuitive, but it does seem to be logically defensible. It works, if you like, logically, albeit that it's not what we normally think of as, you know, how identity works through time. So why is it counterintuitive? So if Ted goes to jail, he's definitely not the person who committed the crime, that's for sure. But maybe he was that person. Well, if he was that person, that's a good reason for him being in jail, if you believe that people should go into jail for crimes. So counterintuitive, but not an insuperable problem. Similar thing, between 1996 and now, there have been loads and loads of TEDs. Right? Now, the thing is, what constitutes the stage of a person? Now, this is rather controversial, but we don't need to go into it in detail, but you could think of the stage of a person as being something like what you are in the moment. And the moment is, you know, it's often referred to as the specious present. It has a time span of, it's less than a second, because within a second you can perceive something and react to it, right? But when we go to the cinema, the images pass 24 frames a second, and it seems like smooth movement. If it was 10 frames a second, it would flicker. So that's hence the name, the flick. So that's what my dad and mum used to call it, going to the flicks. So roughly speaking, you could say maybe there are 5 TEDs a second, okay? So between, you know, there's been a hell of a lot of TEDs since 1996, but each of those TEDs was an earlier TED. So TED now, he was those TEDs, okay? So he was each of those TEDs. He was not all of them together. He was, to each one of those previous TEDs, he bears a relation, he was that TED. So again, counterintuitive to think of all these TEDs. At the same time, it's not logically insuperable. And so temporal counterpart theory is an accepted part of modern metaphysics, what philosophers call metaphysics. It's a theory available to be used if you want to put it to use. And I think we can put it to good use. So let's go on to the next slide. Okay, so TED history was hypothetically linear, okay? Hypothetically, because if this splitting idea is correct about quantum mechanics, then TED's splitting all the time, like all of us are. But what we're concerned about is Alice, and Alice's history is not linear, it's dendritic, right? So go to the next slide. And so the scheme works perfectly well to describe how Alice can come to be Alice up and Alice down, because Alice will be Alice up and Alice will be Alice down. She bears, Alice now bears the relationship will be to the future object, which is, or the future person, which is Alice up, and to the future person, which is Alice down. She's a past temporal counterpart of Alice up and Alice down. Alice U was Alice, she's a future temporal counterpart of Alice, and Alice D was Alice, she's also a future temporal counterpart of Alice, okay? And something important to bear in mind is that this does not imply that Alice will be a pair of people, because the pair of people, Alice U and that, is not the future temporal counterpart of Alice. The future temporal counterparts are stages in her history, and Alice up and Alice down are the two future stages in her divided history. So we've solved the problem, okay? How as counterintuitive as it may be, it solves the problem of how we can make sense of that Alice will be Alice up and Alice will be Alice down. So now we can go on to the next slide. Okay, so now we've got the next question. How can branch weight be probability? Okay, thinking about it again, we're inside the trunk of the tree. There are we're inside these two tubes going off, one's twice the cross-sectional area of the other. How this doesn't seem to be anything like what we think of as probability. How can the area of these tubes be probability. It's that which we now have to make intelligible. So let's go on to the next slide. And so what we're going to do is just, in this next couple of slides, we're going to just take a slight detour as a way of sort of softening the ground for what's to come. And what we're going to think about is an unstable particle. For example, a free neutron, a neutron which pops out of a nucleus in some nuclear reaction. It's unstable. It's unstable, and it has a half-life of about 611 seconds. And what that means is, if you watch it at any moment, if you watch it, it's a bit excessive. So, but anyway, between any time the time that it comes out of the nucleus, there's a 50-50 chance that in 611 seconds it will decay. 50-50 chance. That's what it means by that was what half-life means. Okay. Now, if that process is stochastic, right? And stochastic, it means if it's just purely a chance process, if it's like there's a little demon inside the neutron, which is sort of spinning like a big roulette wheel or throwing dice, you know, and then he's throwing a handful of dice, and if the handful of dice all comes up 6, that's it. It splits, right? That's the idea of the stochastic idea. It's the idea of pure chance, but of randomness, but not exactly randomness, because it's randomness which is constrained by probabilistic law. And that idea, I think we have to say it's intelligible, because lots of physicists believe that that's what's going on. I think a lot of physicists would say, well, you know, it's just random when the thing decays, but you know, there's a probability of a half that it'll decay in 611 seconds. That's it. And also, it's intelligible. There's an objective probability. Okay, objective because it seems on the face of it. I mean, people have arguments against this, and people who work in quantum mechanics say, well, no, there's no objective probability. But on the face of it, this property of the neutron of decaying and having a half-life of 611 seconds seems to be an objective probability of the thing. I mean, the same thing goes for radioactive sample. You know, people talk all the time about half-lives of various sort of radioactive substances. It seems to be a property of the substance, you know, so it seems to be out there, an objective property. And what is the objective property? Well, it's 0.00082 per second. It pops out of the nucleus. There's a probability, it's a small probability, that it'll actually decay within 1 second. Okay, it won't take 600 seconds, it'll take 1 second. And that's the probability. And when it does so, what does it do? Well, what happens is that it emits what's called a W boson, and then this W boson splits into a neutrino and an electron, and in the process, the neutron becomes a proton. We'll go on to the next slide. So again, we're continuing in this softening the ground for what's coming. So just supposing this process were dendritic, okay, rather than stochastic, then it's a continuous process on a time scale of about 10 to the minus 23 seconds. Why 10 to the minus 3 seconds? Because that's the time it takes light to traverse a nucleus or a neutron. And roughly speaking, it's the amount of time it would take to even begin to see that it decayed, if you like. So we've got this idea, all elements of the superposition, all branches are actual. So even after 10 to the minus 23 of a second, there's a very small probability that it would decay. So there's a superposition of exterior environment containing undecayed neutron and exterior environment containing decayed neutron, a superposition with 2 elements, which is a pair of relative states. So like a length of rope which is slightly fraying along its length, a free neutron splits into a decay branch of weight 0.82 times 10 to the minus 26 every 10 to the minus 23 seconds. So it's just like, think of you're thinking of the cross section of this rope, which over a certain length, which corresponds to 611 seconds, there are tiny little threads coming off all the time. I mean, every second there are 10 to the 23 little threads coming off. And after the whole time, the 611 seconds is part, the cross-sectional area of the rope is now half what it was at the beginning. So from this point of view, the decay isn't a sudden, spontaneous one-off process. It's going on all the time, okay? So the neutron will, there's some probability, but it's small, that the neutron will just keep being a neutron for a day, a year, a billion years, if you like. It's a very low probability, but it's not zero. Let's go on now to the next slide. Again, but this doesn't solve the problem. I mean, it was just softening the ground. I mean, so how can branch weight be objective probability, given that, what I hope we can agree is that the concept of objective probability is intelligible, even if there are arguments against it. It seems to be an intelligible idea. So how can we understand the branch weights as being probabilities? So we go on to the next slide. Okay, so now we begin the process of what's known in the trade as a thought experiment. And thought experiments have a rather sort of interesting history, both in science and philosophy. Some people rail against them, but they do seem to have their uses. But anyway, that's what we're going to do. We're going to consider a hypothetical infinite set of stochastic and initially parallel universes, each containing a copy of Alice. Why do I say hypothetical? Because I mean, if this is going to work out, if ever it's right again, then there's nothing is stochastic. It's a figment of the imagination. But we're going to just suppose it seems to be an intelligible idea. So it seems to be an intelligible idea that we could have a lot of universes which started off exactly identical in a big respect. And how can we have a lot of them? Well, because in a way it seems a contradiction in terms of a lot of universes. Well, remember, we can come back to Bernard here. Bernard told us about the observable universe having a horizon, but there's loads of stuff beyond it. There could be a really huge amount of stuff beyond it. There are about 10 to, current estimate, 200 billion galaxies in the observable universe. There could be zillions and zillions and zillions of galaxies out there, and perhaps a countable infinity of galaxies out there. And actually, so that means that there could be an exact copy, not a copy which is made, but just by permutation, an observable universe is out there, which is exactly like the observable universe which we see at the moment. And in fact, Max Tegmark, who Bernard mentioned, has actually made a calculation of if it were infinite or very, very, very big, then what would be the average distance between observable universes, which are exactly like ours, right down to the last detail. And it comes out with an enormous figure. It comes out, as I remember it, it comes out 10 to the power 117 meters. And in fact, the figure, the numbers don't change much if you talk in terms of meters or light years or parsecs or whatever you like. It is an unbelievably huge number. But there you are. Within cosmology, it's currently understood there could be any number, and perhaps an uncountable infinity of observable universes, and that's all we need for this thought experiment. So in each one, we've got Alice about to do her measurement, okay? In each one, it's you can't quite see, but she's there in front of the Stern-Gerlach apparatus, and the electron is saying, measure my spin. And go on to the next slide. And so what will happen is that because it's stochastic and because the probabilities are 1/3, 2/3, this set will, this is using the sort of mathematical terms, the set will partition into subsets of measure 1/3 and 2/3. Now, this idea of measure, you can just think of it as proportion. Here I've shown it as proportion. We had 9 universes start off, we've got 3 have gone up and 6 have gone down. So that's the measure for this. When you've got a finite set, the measure is the proportion, okay? When you've got an infinite set, you've still got the concept of measure, but it's not like the concept of proportion. It starts to get philosophically more difficult, but it's manageable as well. Now, we go on to the next slide now. So these subsets, they're by definition the probabilities, the objective probabilities, because we're assuming that these are stochastic universes, and in these stochastic universes, there's an objective probability of getting up or down. And by definition, the measure of the subset, I should have put subset measure, the measure of the subset are the probabilities. And what's the reason for that? It's because that's a consequence of what's known as the law of large numbers, which is an assumption which is fundamental making statistical measurements. I mean, we're all familiar with this. When you do any sort of survey, polls, for example, whenever you want a statistic, you want as big a sample as possible. You know, the bigger the sample, the more accurately you can expect your measurement of probability to be. Why is that? It's because you assume that the larger sample you get, the more the proportions will reflect the probabilities. And if you extrapolate that to an infinite set, then by definition, the measures of the up and the down universes are the objective probabilities. So the same thing. The probabilities by definition, what these measures would be if, per impossible, you could do, your example could be infinite. So we go on to the next slide. But the subsets are branches, okay? So, I mean, so what I've said so far, I mean, it's just saying the obvious, really. I mean, of course, if you've got a stochastic universe and the probabilities are 1/3, 2/3, if you take an infinite set of them, then of course you'll get measures 1/3, 2/3. I mean, that's obvious in a way. And in each one, Alice has a linear history. Each subject will be seeing up or down. And now this, we'll come a bit more about this. This is the way the many worlds with divergence sees the issue. Many worlds with divergence doesn't have the splitting. Many worlds with divergence has lots of worlds, but each subject is in one world and has one future. Let's go on to next slide. Right, so, okay. Can we just go back to the previous slide for a second? Okay, because I've sort of jumped ahead of myself. Because to introduce the next slide, what I'm going to do is just talk about a very famous thought experiment in philosophy of mind, which is profoundly related to what I'm going to say. Now, this was a thought experiment which was invented. I think there's some idea that there were earlier ideas similar, but anyway, in its modern guise, it was invented by the Harvard philosopher Hilary Putnam in 1975. And there have been lots of variations on this idea, and it's had a huge influence on philosophy of mind and still does so. This is still controversial, but a lot of people who work in philosophy of mind these days, what's called analytic philosophy of mind, take this experiment, thought experiment, very seriously. Okay, So what I'm going to do is describe a version of this, which I've sort of just adapted to make. It's not exactly like the one that Putnam talked about, but it's similar, and it'll make things a bit clearer, I think. So what you're going to do is you're going to think about two planets which are completely isomorphic. They're completely the same in every respect, except one, which is that, I mean, they're Earth-like planets, right? So they're Earth-like planets. On one of them, all the candles are not made out of wax. They're made out of some substance which we'll call W. And on the other planet, all of the candles, they're not made out of wax either, but they're made out of a different substance, which is called, we'll call X, okay? Now, on the W planet, we're going to have a subject, and we're going to call her Wendy. And on the X planet, we're going to have a subject, and we're going to call her Xanthippe, okay? And Wendy and Xanthippe are what you say doppelgangers, yeah? Their bodies are completely atom for atom, but they're not copies. I mean, they're identical, well, they're copies in the sense that they're just like what copies would be, but they haven't been copied off one another, okay? They're exactly the same. Okay, and so the argument goes like this. Supposing Wendy is thinking about, she's thinking about the substance. Oh, and there's another little thing to add. We're thinking about these planets, they're a bit like Earth in the 18th century before anybody discovered chemistry. So people weren't able to do chemical analysis, right? So we got Wendy, and she's thinking about this stuff, this funny stuff that candles are made out of, and Xanthippe, of course, she's doing exactly the same thing over on planet X, and she's thinking, yeah, what I wonder about this stuff that candles are made out of. And the argument goes that what Wendy is thinking about is W stuff, and what Xanthippe is thinking about is X stuff. Now, objections might crowd to the mind, but I can't go into all the details of it, but suffice it to say that arguments of this sort have a great influence, and some very bright people have gone along with this argument, and some people who really didn't want to go along with it got sort of pulled along kicking and screaming and to accept it. The conclusion which is drawn from this is the way that Putnam put it: meanings aren't in the head. The idea is that when Wendy's not thinking about the same stuff as Xanthippe is thinking about, so her mental content isn't the same. Wendy's thinking about X, Wendy's thinking about W, and Xanthippe is thinking about X. So they're not thinking about things, they've got different thoughts. There are different thoughts in their mind, but their brains are completely isomorphic. So the idea is that meaning, as you know, Putnam has put it, meaning isn't in the head. Thoughts aren't in the head. You have to take into account the history and environment of a subject to understand what thoughts they're entertaining. This is a very widespread view. It's known as semantic externalism, and it's very widely held. Now, there's a way to counter this, and this is what's leading to what's coming. There's a way to counter it, which is very strange. And again, it's very counterintuitive. But the thing is, if we're ever going to get to the bottom of quantum mechanics, we're going to have to be prepared to put up with some ideas which are counterintuitive. So what we're going to do is, we imagine we're looking at, this is sort of an interpretive exercise. On the mind's eye, we're looking down from these two planets from above. And the normal thing is to think, well, each doppelganger is a subject. Okay, states of their mind might be very similar, but okay, a bit different, but each one is a subject. Well, you can say, well, no, actually, we can interpret this situation differently. There's a single subject. We're going to call her Xanthippe. Okay, Xanthippe is a single subject, Xanthippe, and there's a sense in which her mind spans the two planets, but there's no sort of causal connection required, okay, because the isomorphism, the similarity between the planets, it's just being presumed. There's nothing no causal connection holding it in place or anything like that. And we're going, and the thing is that when Tipper is holding a candle in her hand, what we see is there's one doppelganger holding a candle in its right hand, let's say, and the other doppelganger holding the candle in the right hand, and they're both, you can hear the sounds coming out of the mouth. I've got a candle in my right hand, those sounds. But instead of interpreting those sounds as coming from two subjects, we interpret them as being expressing the thought of a single subject when Tipper. And what she refers to is a composite of the two candles, and what sort of composite we'll come to in a moment. And then the idea is, I have to say, it's a very strange idea, but it does seem to be defensible, and it has been scrutinized by some pretty capable people, and it does seem to pass. And then the idea is, okay, supposing when Tipper, she discovers chemistry and he does chemical analysis, what happens? She does chemical analysis on this object, which is a composite, and she splits into Wendy, who finds that the calculates W, and Xantipper, who finds it's X, okay? So the analogy with the Everettian splitting is obvious, okay? But the problem is with this argument in the context of philosophy of mind is that it's so weird and so counterintuitive that it just seems like, a crazy way of trying to stop the force of the idea of semantic external. I mean, it seems like, okay, well, you've really scraped the bottom of the barrel if you come up with that idea to try and, because the opposite of semantic externalism is semantic internalism, which says, well, no, actually, the thoughts are exactly where we always used to think, well, a lot of people used to think they are actually inside their head. That's the opposite. And this seems like just some crazy last-ditch way to try and save that idea. So now we can go on to the next slide. And so we consider again a hypothetical infinite set of stochastic universes, but now suppose that a single Anis inhabits them all. So this is where I'm afraid it gets a bit personal, because I introduced this idea to the context of physics in this paper, which was entitled Objective Probability and the Mind-Body Relation in 2017, and I called it The Unitary Interpretation of Mind. We go to the next slide. Right, so we've got a single Alice now, and these are still, we've still got an infinite number of stochastic universes, remember. Her universe is the set of all these universes now, and it's a sort of multiverse. Her universe is composed of universes, so it's a multiverse in that sense. So we've got this idea of a set. Well, now, again, you can go into this perhaps more later, but it can be a bit difficult. But the idea of set is fundamental in mathematics. There was a revolution in mathematics towards the end of the 19th century, instigated by somebody called George Cantor. And it seems that all of mathematics can be understood in terms of set theory. And the idea of a set is just rather like the idea of a collection of things, except that it's different too. So let me just say this, that people, I mean, this sort of analysis of mathematics is called mathematical logic. And one of the prime exponents of mathematical logic was a philosopher now dead, another Harvard philosopher called Willard Van Orman Quine. And he, for the life of him, would have preferred it if he could do mathematics without sets. But he thought there's just no way you can do without sets to do mathematics. You have to be committed to this idea that there are such things as sets, but they're sort of as abstract objects, right? So people who know about sets and so on say, if you've got a pair of apples, the set of the two apples isn't the same thing as the pair, right? The pair of apples is, or you can call it the aggregate, or philosophers call it the mereological sum of the two apples, okay? That has a weight of two apples, right? But the set of two apples, that's an abstract concept. It's an object, according to Quine, it's an object, but what it's generally taken to be an abstract object, okay? So it's not something which exists in space and time, but it's an object nonetheless. It's the sort of, it's the stuff out of which mathematics might be made of, let's say. But then, of course, philosophy of mathematics is controversial too. So let's go on to the next slide. Oops. Okay. So what Alice takes to be her body is a set of bodies, okay? And Alice is a little girl, 9, 10 years old. She might weigh 30 kilos, right? So Alice in her multiverse, she weighs 30 kilos. But then we've got an infinite number of Alices who all weigh 30 kilos. So it has to be that the set of Alices, it's not like the mereological sum of all the Alices, not the aggregate, because that would have infinite mass. So it's got to be but it can't be an abstract object either. It's got to be an object. For this interpretation to work, it's got to be an object which has a mass, but it has the mass which all its elements, because we call these a set. I mean, it's a bit confusing because we talk about superpositions having elements as well, but we talk about sets having elements, and there's a different use of the term element. But all these little Alices at the bottom, they're elements of the set, which is Alice's body as it is to her, the situated subject in her multiverse of stochastic universes. Let's go on to the next one. So same thing goes for the apparatus. Her apparatus is a set of apparatuses. And the next slide. So same thing goes for the neutron. That's what she takes to be a neutron in her alignment is a set, an infinite set of neutrons. And the next slide. So in this setup, Alice splits, and she splits into branches which have probability 1/3 and 2/3, right? Because as we saw, the subset measures are the subset measures of these two. These are now branches because Alice splits into them, okay? Her point of view is like the point of view we started off with. She's splitting into two branches, but now these branches, they don't just have weight, they have probability. I mean, they are by definition the probabilities of the outcomes. Now I'm going to the next slide. Okay, so now there we were consisting stochastic universes, right? But the whole point of the exercise, the whole point of Everett's idea is to replace this idea of a stochastic process with the idea of a dendritic process. So we don't want to have them to be stochastic universes. So we need to replace the stochastic universes with deterministic universes, okay? Each universe, it has to be that the future is completely determined, okay? But nonetheless, this set of universes partitions in the same way as stochastic universes would do. Now that can seem paradoxical, and we could come back to that, but we'll pass over that moment because we'll go to the next slide. Because a set of universes like this, a set of deterministic universes which partitions in the same way as a set of stochastic universes has already been suggested by David Deutsch, who was, you may well have heard of. He's got quite a sort of public profile associated with quantum computation, and he introduced this as an idea of a way of understanding Everettian theory in 1985, thinking about a set of universes which partition in this way. I was actually at a seminar he gave in Oxford on that paper at the time, which was, I mean, I was interested already in the theory at the time, but it was what he said really sort of whetted my appetite to take more interest in it. It was being introduced in a different way by Simon Saunders and David Wallace, also very much in the camp of Everettian theory. It's a different way of doing it from David Deutsch's, but it's quite similar in some ways. And again, by Simon Saunders in 2010, a bit different from what he suggested with, together with David Wallace, but a bit in the same vein. Okay, so it's this idea of a set of deterministic universes which partitions in the same way as stochastic. And then over on the other side, we have somebody from a different camp. This is from the pilot wave camp. And he suggested, not very seriously, it was rather tongue-in-cheek. It was a way of sort of getting back at Everett theories, because David Deutsch, at one time, he came out with this quip that pilot wave theory was many worlds in denial. And so Anthony Valentini wanted to come back, you know, in fact, well, I won't go into that. Anyway, so now we've got a set of deterministic universes, but actually they're all pilot wave universes, okay? And that introduces an interesting extra to the subject, but I'm not going to attempt to go. It's a set of, what I will say is that a set of pilot wave universes which partitions in the same way as a set of stochastic universes is more plausible than what these other suggestions are. So now let's go to the next slide. Okay, so that means that Alice splits two in this situation, because it's just the same argument as before, because if the set of deterministic universes partitions the same way as stochastic universes, then the subset measures are the objective probabilities for the same reason. So that now we've dropped the idea. We used the idea of a stochastic universe to sort of as a ladder, but now we've kicked away the ladder and we've just got deterministic universes, and we seem to now got to making it intelligible that branch rate actually is, or could be, well, it's intelligible that, not that it, but branch rate is probability. Should we go to the next slide? So, is Newtonian case stochastic? Okay, well, if it's stochastic, then it's a process which lacks a mechanism. And that's a very weird sort of thing, because all scientists and all other branches of science are all looking for causal mechanisms. Biologists, chemists, they're all doing it. But not quantum physicists, if they believe in stochastic processes. Why? Because there's this, you know, Albert Einstein, quite famous quip saying, God doesn't play dice. His point was that there isn't some little demon inside the neutron, you know, throwing handfuls of dice. That's not a plausible mechanism. No, I mean, it's just a stochastic process simply is a process which lacks a mechanism, and Albert didn't like that. And here's a quote from Albert. This comes from a letter that he sent to the Royal Society to be read out at sort of celebrations, if that's the right word, of the 200th anniversary of Newton's death, which is in 1927. And it's published in Nature. And it says, he said, "May the spirit of Newton's method give us the power to restore unison between physical reality and the profoundest characteristic of Newton's teaching, strict causality." Okay, strict causality is what we have in the partitioning set of deterministic universes. So is it stochastic or is it deterministic and dendritic? And we can go on now to the last slide in this series. Next slide. So if it is, okay, so I'm hoping nobody stopped me. So I'm hoping that perhaps people are a little bit convinced that actually maybe this idea is intelligible, even if it's not plausible. But if it is intelligible, and if it actually turns out that in the end, everybody starts to agree that that's the right way to understand quantum mechanics, then so what? Then what are the consequences? So that's rather gone on a bit more than I intended, really. But I mean, there was the initial, but anyway, we've still got more than 35 minutes to talk about this. So we could start off by, if anybody wants to have particular questions about difficulties with what I've said so far, and then it would be good to keep some time to go on to consider what we think could be if it really were the case that here we are on Earth and we're all splitting all the time into all these futures which we thought were physically possible, which they're really all actual. Does that have any consequence? Does it make any difference? I mean, according to the argument, the branches are all still probabilities, so we're still talking about probable futures. Okay, but they're no longer alternative possibilities, they're just all actualities. So now I'll leave the floor open now.
Oh, thank you so much, Paul, for that fantastic presentation. It was really thought-provoking, and definitely to sit on that for a bit. It was a lot of content there, so thank you so much. Before we open it up, I'd just like to invite in Shantena, the director of the Paris Center and the chair of this event, to see if he has any contributions to make, maybe a bit shorter, but just to allow some people for the audience. Are you just muted at the moment, Shantena?
Yes. Thank you, James. Thank you very much, Paul, for, I would say, a real tour de force in helping us to absorb as intelligible this very unintuitive, not immediately perceived as such. And I would like to have your opinion or your comments on. I'm rephrasing, hopefully shorter, the question I asked Bernard yesterday. Concerning the decoherence understanding, the decoherence interpretation of quantum physics. I see that there's one aspect of similarity. The wave function evolves in a unique way. There is no collapse, and but there is an equivalence between Alice seeing or up or down, and Alice seeing and both up or down. The equivalence can be proved on various levels. The normal argument relates to the macroscopic nature of the apparatus and the environment, so on. I have my own slightly different view, but let's not go into that. I would just like to have your comments and about these two different approaches.
Okay, well, look, yeah, I know that earlier, I mean, I wasn't able to, well, I only learned about it sort of afterwards, but I know you've had sessions talking about Bohmian theory quite a lot. And so you've been talking quite a lot about pilot wave theory. And of course, so what you're talking about, in pilot wave theory, you've got this idea of the Bohmian particle, which is guided by the wave which is manifest as a sort of what they call a quantum potential. And so if you put Alice in there, there's only one Alice, who follows one of the paths of all the possible ways to go. There's only one that the actual particle, the hidden variable particle, goes. And so there's one Alice in there, and all the other ones are possibilities, if you like. They're empty branches in the wave function, that's the expression that people use. In a way, if you talk about equivalence, there's a sort of element of equivalence there. When you're talking about decoherence, yes, indeed. I mean, if we went back to that slide, well, we don't need to go back, so I think everybody remembers it, but the quote from Everett, he talks about, nobody is aware of the splitting because these branches are completely independent. Well, in fact, we know now from decoherence theory that they're not absolutely completely independent, that there can be a vestigial interference between the two. And people, I think David Deutsch, have tried to imagine possible experiments at this stage, not things that you could actually do in a laboratory, but maybe one day do in a laboratory where you could actually get people to split and then recombine them afterwards. That element, the way, if you're thinking in terms of the branching, in terms of decoherence, that leaves a very small window of opportunity for perhaps some sort of empirical justification of the Everettian view, perhaps. But otherwise, I would say what I've been talking about, the intelligibility, I would say that this is entirely a matter of metaphysics. It's entirely a matter of being able to understand some possible way of describing the world such that it would be intelligible, that it could be that we split into these worlds, and that they actually do a property of these branches is probability. Does that make anything clear? I mean, is that helpful?
Helpful, yes. Clear is a strong word, but thank you, Paul.
Okay.
I won't take up more time.
Thank you, Shantina, for coming in, and thank you, Paul, for answering. So yes, now we can open it up. As I said earlier, to ask your question, you can use the raise your hand function on Zoom, which is under reactions at the bottom of your screen, or physically raise your hand, or write it in the chat. I already see we have Bernard has his hand up, so please come in.
Thank you very much. I'm not sure if other speakers should be asking questions, but I can't resist. Well, thank you so much, Paul. I mean, I've thought about many worlds picture, but it's so helpful to have all these actual pictures of all the Alices. It somehow crystallizes the idea. So I found your talk very helpful indeed.
Well,
and I'd like to ask how what you're saying relates to another problem, because you've only been focusing on Alice. Now, the problem which always fascinates me is why I am me rather than you, or Shantina, or James, or indeed any of the other 7 billion people on the planet. And it always seems to me that, a profound, and obviously we're in the domain of philosophy here rather than physics, but it seems to me a profound question which is almost impossible to ask in any normal sort of physical context. Why am I me? Now, when you draw your pictures of Alice and all the millions of Alices in your parallel worlds, it seems to me that's rather similar to the question of, why me? Am I me in one world? Am I James in another world? You in another world? Shantina in another world? So is that a separate problem, or is it the same problem?
Well, look, it's very interesting, and I have to say, Bernard, I very much appreciate your talk as well, and particularly your reflections towards the end of it. So that was very good. Well, look, I think it is very pertinent because, look, this unitary mind idea is very, very strange. I remember as a kid, I was a great fan of The Sky at Night, Patrick Moore, and I remember him once saying, well, I'm sure that out there in a distant universe, there's a planet just like Earth, with a planet just like you and me, doing just what we're doing. This idea, and it's been there's a French Thomas Lepelletier, who's I think hasn't been translated, a book called Univers Parallèle. And the history of the idea of parallel universes and this sort of recurrence and this sort of thing goes back quite a long way. But so this idea has been around. Imagine there's an exact copy of Earth, zillions of light years away, somewhere out there, way beyond our event horizon. And it's got somebody who's actually isomorphic too. They're having exactly the same experiences you're having. And of course, we normally think of them as, well, okay, well, that's not me, that's another person, and they're way off in the distance. What this unitary mind idea is saying, well, actually, no, that's the intuition, but you can overcome that. You can say, well, actually, no, there's actually just one person there, and what we take to be one planet is actually two planets which are sort of superimposed on each other. And there is another sort of interesting connection here as well, because in the Star Trek, we have when Captain Kirk is beamed up to Starship Enterprise in the star, what's it called? I mean, the whatchamacallit series. Anyway, you've got this idea that you could be sort of, you could travel by teleportation. So imagine you, and this, I mean, Parfit discusses this quite a lot, and it introduces some very interesting conundrums. And you've got this idea of you're going to go to Mars, and then you step into this transmitter, and what it does, it makes a sort of an extremely detailed sort of readout of the state of your body before destroying it and then sending the information to Mars, where there's a receiver that sort of prints out a copy of your body, and there you are on Mars. Well, of course, if you take the view that the person on that other planet who's just like you is not you and they're far away, then you're going to say, well, that other person on Mars isn't me either. That's just somebody else who's just like me. So the unitary mind idea, if you put it in that context, that argues for, well, actually, you could travel to Mars by teleportation because actually it would be you. So there's some interesting sort of connection there, but is that on the same wavelength as your question or not?
Well, sort of, yes. I'm keen on the concept of one mind, in the rather mystical sense that we're all fragments of one mind, and the question is, how does the one mind fragment into little minds? And the question is whether that one mind is what you're calling the unitary mind.
Absolutely not. No, absolutely not.
Yeah.
No, absolutely not. No, I mean, no. For me, you're different from every other person on this other 7 billion people on the planet, because there's different stuff going on in your brain, and of course, each one of those people can say, "Oh, well, why am I me?" But in a sense, you're me, you're you because of what stuff. That's what's going on in your brain, giving you the experiences you have. Yeah, and the unitary mind idea is that, so if there was another being somewhere had exactly the same stuff going on as in your brain, well, then actually that would be you too. But in order to make that idea work, then you've got to introduce this idea, as I was saying then, of this what you're referring to as the set. So if there's a copy of Earth somewhere else, and I'm actually both, then what I call Earth is a set of two planets, and it has to have the same mass as one planet, the mass of it. So it's a very different idea from the one mind idea. But I look forward to your final lecture when you're going to be talking more about the one mind idea.
Well, thank you so much, and I look forward to further discussion, but obviously not now because there are other people I know who want to get in.
Okay, good.
Thank you, Bernard, for coming in. Next, we will go to Basil. You're just muted at the moment.
Yeah, I was expecting to be second in the queue, actually. So I'm sorry.
I made you go first because I know you have to leave early.
Okay. Oh, thank you very much indeed. Yeah. Well, Paul, thank you very much for that talk. Now we're in an interesting situation. My first remark is always philosophers.
Right.
They're slippery with their words, aren't they? And one wonder, yeah. So let me leave that go and just say I'm a physicist. And one of the things we are trying to do at the moment, I'm trying to be positive now, Paul, is to look at the recombination of wave functions in the laboratory.
Right.
And one of the difficulties I have is that I mustn't mention the words many worlds in the laboratory. Otherwise, I would be banned for life. Because as you know, experimentalists will not tolerate that particular view of things. But what I want to do is to actually get a little bit deeper into Bryce DeWitt's point of view. I was actually at a lecture when Bryce probably came to London, or maybe I heard him lecture somewhere else. It was long before the days of Zoom and so on. And he came bouncing in saying, "Oh, I've actually found the best thing since sliced bread." And then gave us a talk on the many worlds. Now, I had been reading Bryce DeWitt's work, and he struck me as a very serious, complicated man with much interest in the mathematics. And so and then I found just the other day a paper by Bryce DeWitt. It was in the same volume of PhysRev as David Bohm's famous hidden variable paper, but it was 2 issues later. And there he talks openly about the quantum potential, showing that the quantum potential is a necessary feature if you assume principle of general covariance, because he was looking at what happens if we do quantum mechanics in a curved space-time. Now, my problem therefore is, why does he suddenly, after developing all the things which are very close to David Bohm's, but much more mathematically inclined, which ties up very nicely with both Feynman's propagator work and more particularly Schwinger's propagator work. Because Schwinger actually says you can always make a field theory look as if a particle, in quotes, is following a trajectory, in quotes. So there's a very interesting region of exploration there. But suddenly, Bryce comes in and says, "Oh, well, I believe in the many worlds interpretation." Can you throw any light on that sudden change? This is what's puzzling me.
Well, I can. I mean, maybe I can take 1 or 2 guesses. Just before saying anything about that, I mean, I was just in passing, Wheeler. I mean, he wrote a paper together with Everett's 57 paper, and where he was really sort of saying, he was very effusive, saying, there are times, when you have to really take on perhaps a profound change of world. Really, really, he was really seriously interested in it, but at the same time reticent as well. And it was interesting. Somebody told me that they talked to Wheeler in the 90s and asked him why he'd sort of given up on Everettian theory, and he said, "Oh, it's just too philosophical." So it does seem that the philosophy just can't talk about Everett without bringing the philosophy. But to answer your question, I mean, perhaps one reason is that, I mean, as you everybody's aware, with pilot wave theory, there's this problem of non-locality. The idea that there's a privileged rest frame. We know that it's not in conflict with special relativity, but we know that it's, yeah. Also, he might have been uncomfortable with the idea of hidden variables. He might have become to think, well, having hidden variables is just sort of having I don't know, sort of something occult about it or something like that. I mean, they're possible suggestions. I don't know. I mean,
well, can I come back?
Yeah. Well,
one of the tragedies for David Bohm, I think, was that he actually changed the title of his paper. I don't know how many people are aware of this, but recently a first draft of his paper turned up in the De Broglie archives.
Mm.
And it was entitled A Continuous and Causal Explanation of Quantum Mechanics.
Mm.
Now that would have been fitting in with everybody else. Going into hidden variables immediately went into that tremendous debate, heated debate between Bohr and Einstein of whether hidden variables existed or not. The trouble is with Bohm's work, there are no hidden variables. There are variables which are used in the Schrödinger equation and they are interpreted as a hidden variable, but they are not new additional variables which will be able to explain the statistics of quantum mechanics, for example.
So are you saying then that from the point of view of Bohmian theory, it's not true that in a one-shot interference experiment with the electron is actually going through one slit or the other? I mean, that's that's the way I understand normally pilot wave theory.
Yes, I know. I have been doing a lot of work in the last 4 or 5 years, and I have now come to the conclusion that no, let me put it this way: what I was doing when I first came across the Bohm theory, and I was introduced it by 2 students. I didn't, because I thought it was all a load of crap. And the students said, "Why is it a load of crap?" And I had to explain. And they said, "Oi, oi, oi, you haven't read the paper properly." So I went back and read it and suddenly found that, yes, I hadn't read it properly and that what people had been saying about it was totally wrong. The question I then raised was, what is the meaning of these trajectories? And the meaning I have now found comes from the way Schwinger was going, and it's very closely related to one of Schwinger's papers where he makes this comment, which I commented on earlier, namely that you can always make a field theory look like a particle following a trajectory. I'm not a Bohmian mechanic, please. I don't believe that at all. It's not mechanical. Quantum mechanics is organic. But sorry, look, I'm lecturing. I'm sorry. I've said enough. But it's just the puzzle of the DeWitt sudden change.
Right. Yeah. I can understand that. Yeah, it'd be interesting to know. What, because I mean, well, yeah, let's leave it because other people have got questions.
Yes, please.
Well,
thank you.
Thank you, Basil, anyway, for participating. Next, we will go to Niels.
Okay, thank you. I find all this very puzzling because my background is a more down-to-earth background. And in that background, we operate in a computer model of moving moving people, you could say that there must be some relationship with that. That is like in quantum mechanics.
Mm.
They're parts moving, and if you go back to the initiation where the black body from I can't remember his name now. That was more like these quanta moving, and they had different, in a sense, different sizes and things, depending on the frequency of things. In the transport model, that is not generally accepted by my peer groups. I'm now retired. I did this 30 years ago, and it's been very good. But I'm thinking also of Gödel's incompleteness theorem. So when you talk about logic and mathematics, that can't always finish the circle, if you like. And so
just to cut you off at that point, so you think the concept of set, the concept of a set of two apples being a different thing from the aggregate, the pair of the two apples, that's a dubious concept?
Well, I'm not saying it has its use, but not necessarily it depends on the context, I think.
Right. Okay.
And
I mean,
what do you think about process rather than process is more organic, more, and I think Bohm was going in that direction.
Absolutely. Look, in a way, I was alluding to it right at the end, but if you want to consider this thought experiment with a set of universes which evolves and which partitions, I think the most transparent way of doing it is with a set of Bohmian universes, in fact. Yes. Because if you don't do that, I mean, like David Deutsch, I hope he won't mind me saying this, but when he because I've talked to him about this, when he introduced his idea of this the partitioning set of universes in his 1985 paper, he thought of them as being starting off as completely isomorphic and then partitioning. And I was saying to him, well, yeah, if they start off as isomorphic, then why do they partition? You know, I mean, why would they? Why don't they just stay isomorphic? Because of course, I mean, and he said, well, funnily enough, I was talking about this, and a 9-year-old boy came up and said, he asked me exactly the same question, and I don't think he has a good answer to it. So if you're going to talk about these sets of universes, I think you've got to have a mechanism in there behind this divergence. You can't just start off with them being isomorphic. You've got to have, there's got to be a reason why they diverge. And if it's a set of Bohmian universes, you can find a reason, because they can all have different what would be called hidden variable trajectories, even if Basil doesn't really quite like that word. Right?
Sorry, my earplugs are going out of.
Oh dear.
Thank you, Niels, anyway, for coming in.
Can you hear me now?
Yeah, we can hear you.
I can't hear myself.
But yeah, anyway, we'll move on. Thank you, Niels. We'll go to Alan next.
Paul, thank you for a thoroughly enjoyable presentation, which, yeah, I think I followed most of it. But there's one thing that isn't totally clear to me, and I guess what I'd like to ask is, can you describe the universe before Alice actually does the measurement? because you talked about an infinite number of universes and a set of universes, and her body being a set of bodies. But I struggle with the word infinite. Maybe my misunderstanding. You might be saying, well, the set is infinite, but I'm not sure what that really means. So could you describe reality, as it were, and the individual Alice before the measurement? Thank you.
Well, okay. So the idea would be before Alice, there would be this infinite set of universes, and there wouldn't be Alice in them. There would be, if you go back sort of several billion years, there would be Earth, but it would be a set of universes, the sort of things that we're familiar with. I mean, what we call the observable universe. I agree with this idea about infinite starts to get difficult, and it takes it into sort of deeper discussions in a sense. The trouble is, if you've got a very big set of universes, it's less troublesome because you can think of the partitioning in terms of proportion. But the problem is then that you cannot identify the branch weight with probability, because as we know, you can't identify probability with measurable frequencies. They can only you've got to have an infinite sample for it to make any sense. So I would totally admit that having an infinite set creates problems. I mean, I don't think they're insuperable problems, but it certainly merits further discussion about, you know, what's the sense of, as you can put it, somebody put it to me, Chip Sebbins put it to me like this: is what does a measure on an infinite set measure? And that's a reasonable question. I think there's a reasonable answer to it, and maybe I shouldn't attempt to go into that now. I could do very quickly. Imagine you've got an urn which has got one third blue tokens in it and 2/3 green tokens, right? So it's perfectly straightforward, the measure of blue tokens and green tokens. Go to any finite number of similar urns and you've still got a perfectly clear sense of what the measure is in terms of proportion. But now if you say, well, look, could an infinite number of such urns exist? Well, according to current cosmology, as I understand it, Bernard could correct me, but yes, a countable infinity could, because as far as we know, there could be an infinite number of galaxies, a countably infinite number of galaxies beyond our event horizon. So it could be a countably infinite number of observable universes with urns in it. And then in that sense, the measure of the blue tokens and the green tokens in the infinite set is there's a strong relation between the measures in the infinite set and the proportions in the finite set. But I should say no more than that. It's just a sort of intuition pump, if you like.
Thank you.
Thank you, Alan, for your question. Don't see any hands up, so I'll just read something from the chat that came. So the question comes from Gordon, and he asks, regarding quantum tunneling in the Everett approach,
yes,
wouldn't this suggest a swap of a particle between universes?
No, I don't think so at all. I mean, we're the quantum tunneling. I mean, how can I put it? If you we think about a two-slit experiment, and you fire off an electron. Now, the electron, the wave function of the electron is sort of, it concentrates the probability. It's like you think of it in a cathode ray tube where you've got a beam of electrons. The wave function of the electron is concentrated in a certain direction, but it's not zero, and there's nowhere where it's zero. So so an electron is emitted, right? And wherever it comes into contact with a detector on a detector screen or something, there's a branching. There's a branch where a detector fires. How can I put it this way? Imagine a two-slit experiment, you fire a single electron, it goes to the slits, there's an array of detectors, array of 100 by 100 detectors. So there are 10,000 branches where one of the detectors fires, yeah? But there are also going to be branches where the electron actually doesn't hit the detectors at all. There'll be a branch where the detector, where the electron goes off and sort of at a right angle and has some other effect, which could have some macroscopic consequences. I mean, it could, you know, you could have somebody could be doing the two-slit experiment, and then there could be a Geiger counter sitting at way off at a 90-degree angle. And you know, with immensely small probability, the electron that you send off, it doesn't hit a detector at all. It fires off that Geiger counter. So, and the same thing goes for tunneling. I mean, so you put emit an electron and put a sort of a barrier all around it, a spherical barrier all around it. Well, there'll be all the branches where it interacts with different parts of the barrier, but there'll also be a branch where it doesn't interact with them at all because it's gone right through. So no, it doesn't. No, the tunneling doesn't imply any sort of passing between universes. It just means that they're all tunneling is just the branches where the particle doesn't interact with what it goes through, but there'll be plenty of branches where it does interact with what it goes through. Yeah.
Thank you, Gordon, for that question anyway. And I've got a question which is sort of in a similar area. Apart from the origin of the branching and multiverse, how do multiverses interact with each other? You know, yesterday Bernard said that some people saw evidence or something that
absolutely
that multiverses bump into each other or something like that. Is there an interaction between our universe and a parallel me?
Well, okay, so this is quite different from what Bernard was talking about. So yeah, these are his bubble universes, which can sort of maybe bump into each other, brain theory and so on. As I said at the outset, think of us, we're inside a bubble. We're just in one of these bubbles, if you like. And then you get the branching, and then, as I was saying earlier on, Everett talks about them being completely causally separated. But nowadays, because branching is analysed in terms of decoherence, there's quite wide. Not everybody in Everett agrees with that, but quite a lot of people do. It seems to be the mainstream idea, and that implies the possibility of interaction between the branches. So it's not completely excluded, but it's from the point of view of you being only not one branch, unless perhaps you can set up very particular experimental apparatus, maybe along the lines of what Basil was talking about, then it will be extremely, extremely, extremely improbable. So improbable that in the lifetime of the universe, you wouldn't expect for ever to see it happen, that there could be interaction between branches, but it's a very feeble possibility. Yeah. Okay, but then, of course, I mean, all the possibilities happen. So there'll be somewhere in the whole multiverse where indeed these interactions do go on if they can. Yeah.
Okay. Well, thank you for answering my question. I can't see any hands up, so maybe, and we are past the hour, so I guess maybe we should start closing. Paul, do you have any final remarks to give us before we close?
Well, I mean, it's just been a great pleasure to talk like this, and I'm quite pleased that I seem to have had I haven't terribly shocked anybody. Maybe I've managed to keep people on board a little bit, but anyway, it's been a great pleasure doing it, and I'm really thankful for the invitation. Yeah.
It's been a pleasure on our side to have you, Paul. Thank you so much for your fantastic presentation. Really dense and a lot to think about. So really, thank you for that. And thank you everyone here who participated in the chat or asking questions or even just for listening. Just before we go, I'd just like to invite you all to next week, where we've got the second week of multiple universes, where we're going to take a short break from physics. We're going to discuss other disciplines. On Saturday, we have Geraldine Mencina and Mindahi Munoz, who will talk about the multiple universes in Mesoamerican cultures. And then on Sunday, we will have Jean-Francois Benzina, who will have his session entitled May the Force Be Between Us, Exploring Our Multiverse with the Help of Star Wars and Others. So I hope to see you all then. As always, you can contact us on our website, on the Contact Us section, social media, Facebook, Twitter, Instagram, or email us directly at james@parscenter.com to contact me, or Eleanor@parscenter.com to contact Eleanor. Thank you all again for joining us. Thank you so much, Paul, and we'll see you again soon here at the Party Center. Bye-bye.
Thank you, James. Thanks.
Thank you, Paul. Wonderful.